Well, I'd like to be in my office feeding people tea.
Yeah, thank you so much for hosting me there, not in your conference room, at least not too long ago. Well, since we have a few minutes, I guess 5 minutes until it's officially 5 past, and there are a number of faces I see here that I have not yet had the opportunity to meet. It would be cool if those who've already arrived early could be so kind as to just introduce themselves briefly.
I guess I'll start. So I'm Ferran. We met online when I invited you to the seminar. I do computer science and machine learning at CISE with Leslie Kirping and Tomás Lozano.
Are you Catalan?
Yes.
Catalunya triumphant, tornarà se rica e plena, tanno fana questa gente. I'll spare you the rest of the song now, but I have very cool memories from Catalonia back when I was a high school student.
Oh, nice, nice. You were from Sweden, right?
Yeah, I went there when I was, that was my first trip ever by myself abroad. And that worked in the children's camp as a camp counselor, and I was the only person who spoke English. This was I learned more Spanish there than I ever did in school, I think.
Yeah, English is not the specialty in Spain, I think. We're improving, but pretty slowly.
Who wants to go next? So Jerry, you're off the hook because I know you. Who else wants to introduce themselves?
I'll go. I'm Nick. I'm a PhD student at Harvard, but I'm co-advised by Jean-Jacques Slotine at MIT. I'm interested in the intersection of control and dynamical systems and machine learning.
Awesome.
I was an undergrad major in physics, so I have background in a lot of this stuff. So
fantastic. You're wolf in sheep's clothes. Great. Who's next? Aparna.
Oh, sure.
Hi, I'm an undergrad at MIT. I'm currently in India doing remote work.
Sorry, I think there was a bit of a loop because I was streaming the talk on YouTube, and so the YouTube was talking. I'm not sure if you could hear it. And so after 20 seconds, the sound came back from the YouTube back to the talk.
Well, I'm honored that you got up at just staying awake at such a late hour in India to listen to this.
We'll start the talk in roughly 3 minutes. I'll first introduce you for 1 minute.
Perfect. In the meantime, it's really cool for me to get to be introduced to some more of you here, as many as we have time for. So just let's go through as quickly as possible. So if it gets quiet, introduce yourself. Razvan.
Hi, I'm Raz. I'm a postdoc in the CCEL at MIT, working on a machine learning for medical applications.
Vorbesc românește?
Yes, da, vorbesc.
Foarte bine. Vorbesc puțin românește, nu foarte bine. Lumea mică. Who else wants to introduce themselves real quick here before we start? It's much more fun for me as a speaker if I know a little bit more about you.
Hi, I'm Henry. I'm also an undergrad in the computer science department, and I'm here because I enjoyed your 802 class a couple of years ago.
Oh, wow. So you, after suffering through that, you're coming for more torture.
Yeah, I really enjoyed hearing you speak in that class. So.
Well, thank you. We have 1 more minute. I think we can hear from a couple more people. Don't be shy. If you're not the bot and you haven't introduced yourself, just say very briefly your name and a little bit about yourself.
Hi, I'm Jason, a final year PhD student under Eric Domain in theoretical computer science.
Great.
Hi, I'm Peter Solovich. I'm a computer science professor and a lost physicist from undergraduate days.
Once a physicist, always a physicist. Never lost.
Okay, I think we'll start now. So welcome all to the AI seminar. So from a logistics perspective, those on Zoom, you can unmute yourself at any time and ask questions, or you can also send me a private message and I'll read your question. For those listening on YouTube, you can write it as a comment on the YouTube video, and we'll read the questions at the end. Today we have with us Professor Max Tegmark. He's a professor in the physics department at MIT and also a member of the Center for Brains, Minds, and Machines, CVMM, also at MIT. He is known as Mad Max for his unorthodox ideas and passion for adventure, and his scientific interests range from precision cosmology to the ultimate nature of reality in artificial intelligence. He has an incredibly diverse academic curriculum. He did his undergrad and PhD in physics in Sweden and Berkeley, respectively, but he has also studied economics also in Sweden, and he is now a professor in physics, focusing on precision cosmology, for which he received the first prize in the Science magazine Breakthrough of the Year 2003. In 2000, he wrote a very well-received paper on how we do not need quantum mechanics to understand the brain, and we can analyze it from a more classical perspective. And then more recently, he has also focused on artificial intelligence and how we can use it for the benefit of humanity, founding two institutes, the Foundational Quantum Institute and also the Future of Life Institute. Welcome to the seminar.
Thank you so much for inviting me. It's an honor and a pleasure to be here. So as you just heard there, I've spent most of my career doing physics, which is why I'm a professor in the physics department. But in the last few years, I've just gotten so excited about machine learning. I've shifted my MIT research group entirely to be about machine learning. And that's what we're going to talk about today. And that's why I feel so lucky to also get to be part of the Center for Brains, Minds, and Machines here. And today I want to talk a little bit about how these two disciplines intersect, AI for physics and physics for AI. By AI for physics, I mean, how can physicists use machine learning tools to do better physics? And by physics for AI, I mean, how can we actually improve machine learning and AI itself by taking cool ideas and techniques from physics? So a lot of great opportunities, of course, to do better AI, because the AI has just advanced leaps and bounds in recent years, as you are all very well aware of. I mean, just think about it. Not long ago, robots couldn't walk. Now they can do backflips. Not long ago, we didn't have self-driving cars, and now we have self-flying rockets that can land themselves with machine learning. Not long ago, we didn't have good face recognition. And now we not only have that, but we have the ability to even simulate your face saying stuff you never said. Not long ago, AI could not save lives, and now machine learning is already getting so good that it can be really, really helpful with diagnosing prostate cancer, lung cancer, eye diseases, and even win the annual protein folding contest and get really, really competitive results when you compare what the machine learning algorithm said based on the genetic sequence that the protein would be shaped like, and what X-ray crystallography tells you in a much slower and more expensive way, which I think is really going to accelerate drug discovery. And not long ago, of course, AI could not beat us at Go. And now AI can crush us not just at chess and Go, but more interestingly, it's not just crushed the gamers, but also crushed AI researchers like us, right, who had spent decades handcrafting algorithms to play these games, which are now made obsolete by Google's AlphaZero AI that doesn't use any human training data and just plays against itself. So how can all this progress help physics, first of all? Here's a long list I put together of what a bunch of my colleagues in the physics department are using machine learning for to just improve their various physics endeavors. And it's fascinating, the diverse set of things. Right now, for example, machine learning is being used to better detect distortions in space-time in the 22nd decimal place, to discover gravitational waves coming from colliding black holes a billion light years away from Earth. We're using machine learning to greatly improve what we can do that study the smallest building blocks of nature at the Large Hadron Collider at CERN. And physics can, of course, also help AI both in terms of the hardware, in terms of more theoretical software ideas. So on the hardware side, for example, my colleague Marin Suljacic in the physics department, working with Derek England, have done this incredibly cool work on a chip for machine learning, which computes not by shuffling electrons around in 2 dimensions, like today's CPUs and GPUs and FPGAs tend to do, but by shuffling photons around instead, drawing about 1 million times less energy and raising the possibility of getting about 1 million times more compute per dollar or per watt, which I think is very exciting. And for the rest of this talk, I want to focus on how physics can help AI more at the level of ideas and methods. So why do we need, first of all, any sort of help from physics if everything is going so great? Well, partly it would be nice, of course, if we can just make our methods work better in general and accomplish more things. There are a lot of things we cannot do with machine learning. But we also have some challenges that I want to comment on a bit more specifically. So for example, it hasn't only done great stuff, machine learning, right? We all know about the big scandal when some software that was widely used around the country to decide to recommend who was going to get probation and who was going to stay in jail turned out to be racially biased. Not because the people who built this were racist or anything, but because they hadn't understood well enough how the machine learning system actually worked. Similarly, there was no malice behind the Boeing 737 MAX automated system malfunctioning. The designers just hadn't understood well enough how it worked, even though it was incredibly simple compared to most machine learning applications. Knight Capital, the reason they blew $10 million a minute for 44 minutes straight on what was, again, not because they were hacked or anything, or not because of malice, but because they just hadn't understood well enough how their system worked. That's also why all the 3 billion Yahoo accounts got hacked and why Equifax got hacked, because they hadn't understood well enough how their security software actually worked. So Tommy Poggio, my CBMM colleague and sort of the godfather of it, right? He likes to emphasize the difference between the engineering of intelligence and the science of intelligence. And what he likes to point out is that engineering intelligence is very much about just getting things to work. And if you can make profit off of it, even better. Whereas the science of intelligence aims to also understand more in depth how it works. And I'm very interested in this because I think that's a very promising route towards making systems that are ultimately more trustworthy and reliable because we understand how they work. So intelligible intelligence is therefore the slogan of my AI research group here at MIT. You can see at the top what we looked like before the lockdown, and the bottom what many of my students look like afterwards with rectangles around them. And having systems that you can trust is particularly important now as we're putting machine learning in charge of ever more decisions that affect people's lives, right? Where it's beyond just some funny, oops. You really want to get things right. Stakes are higher. So I want to tell you about 4 papers that we've recently finished that all are on the same theme about how we can make machine learning that we can trust better. Let's start off with this one with my former MIT grad student, Tai-Ling Wu, who's a postdoc at Stanford now. And what we did was we started by just training a standard machine learning system, in this case, DeepMind's DQN here, to just do something that looks kind of intelligent and smart. So in this case, playing an old Atari game that many of you recognize from the days of yore. And after a while, even though it sucked in the beginning, after a while it looks like it's pretty intelligent. It figures out this cool strategy that you should drill a hole in the wall and always put the ball there, etc. Right? But how does it really work? Do we understand it well enough that we would trust that it always works at the level we would like our self-driving car vision system to be trusted? Well, in this case, since we just trained this on our little Linux server, we can look inside and see what it's doing. And this is how it works. you take all the colors of the pixels, represent them as numbers, multiply by a big matrix, apply an activation function, multiply by another weight matrix, etc. We have all the 867,488 parameters. Is it crystal clear to you now how it works? Completely useless, right? In terms of getting any intuition that will lead you to trust this system. It would be so much nicer if this were a bit more intelligible, what it's really doing. And when you play a game like this, you actually have a lot of intuition for how your algorithm works. It's not that complicated. The ball always moves in a straight line with a constant velocity, and you can figure out a little formula for where the ball is going to go. You put your power there, right? So what the overall thing that we want to do is first train a neural network to do something useful and smart, and then not stop, but then add some additional automated tools to distill this inscrutable but useful neural net into something much simpler and more intelligible that performs just as well. Some people seem to think that the power of deep learning is inseparable from its being so inscrutable, or maybe even the fact that you can't understand it, there's sort of key to it in sort of a mysterious way. I think that's just nonsense. Just like the paper you alluded to in the beginning here about consciousness in the brain, where some people said that, you know, intelligence in the brain is mysterious, quantum mechanics is mysterious, so they must be related. And I think that's equally nonsense. I think the power of deep learning does not come from its mysteriousness, from its inscrutability. I think it comes from its differentiability. And what I mean by that is, if you're just trying to find the best Python code to play this game, you can't do gradient descent. And you can't just try all possible programs because there are exponentially many. And you have no learning signal telling you if you change your program a little bit by changing the letter R to the letter P here, whether you're going in the right or wrong direction, right? What's so awesome about neural nets is simply that it's any set of parameters defines a valid computation, a valid function, a valid program, and you can get a learning signal to figure out how you should automatically improve it. That's not incompatible with simplicity at all. So I want to start you off by just practicing your own neural networks here on a very simple task. It's a little more complicated than the Atari one because this ball is not moving with constant velocity. The task is just predict where the ball is going to go. So whenever you see any sort of pattern, please just shout out. We're going to make this interactive here, and don't be shy.
Seems to change direction as it accelerates.
Yeah, sometimes it changes direction, and it certainly changes the magnitude of it. It changes its velocity also. So there are definitely, it's like a physical system maybe with forces in it. That's right. What, anything else we can say? And don't make observations even if they're very obvious, because if you're a computer, nothing is obvious if you're given no prior knowledge.
Well, it's obviously bounded in space.
Yes, there seems to be some sort of bounding here. There seems to be borders, right, that the ball can bounce against. What's the shape of the boundary, would you say?
Looks rectangular.
Looks like there's a rectangular boundary where the ball will bounce against. Very good. And what about the forces themselves? Does it seem like it's the same force law everywhere in the picture, or might it be that there's something that are different forces in different parts and different domains somehow?
Seems more circular bottom right.
Yeah, bottom right, you often get this sort of circular motion like you might get in a magnetic field or something like that for a charged particle. Whereas now up in the upper left, there's nothing circular about it. Yeah. So there seems to be.
It's probably the game where you have two fingers and you're trying to bounce it up to collect points, like the game we used to play as kids.
Ah, so you think maybe there's an intelligent agent with some algorithm trying to accomplish something here. So you see how good your own neural networks are, right? You're not just able to make some predictions for where it's going to go, but you're discovering some higher level stuff, even though this is much more complicated than the Atari game. So here's what we did. First, we just did the trivial thing. We just took a feed-forward neural net, put in the last 3 positions and try to predict the next one. Works pretty good. What do we learn about that from about the dynamics? Well, again, absolutely nothing useful, because we just get a bunch of parameters that don't mean anything much to us. So now we take some ideas from physics. In physics, for example, Galileo, in this apocryphal but famous story where he sat in this church at the sermon 400 years ago, his mind drifted away from the sermon, and he instead of paying attention to try to predict everything, he just decided, like what the priest was going to say, he decided to just predict the angle of the chandelier that was swinging a little bit in the wind. He just focused on that, nothing else. And then he timed it with his pulse, and he found the very simple mathematical formula for the period of a pendulum and discovered it's independent of the amplitude, and he helped kick off the scientific revolution, right? So this is the divide and conquer idea, that rather than trying to fit one big neural network or one big model to all the data, let's have an ensemble of models that can each try to just predict some little aspect of some of the data and encourage them somehow to specialize. We're also going to bring in Occams Razor and some unification and other things here. So Occams Razor even is just simply the idea that if you have 2 different models that are equally successful in accuracy for predicting, the one that's simpler is probably going to generalize better. And then unification and lifelong learning we can come back to. So how do we implement Occams Razor in practice? Well, Ray Solomonoff gave this very rigorous definition of description length, which is unfortunately NP hard to evaluate in practice, and it's not differentiable either. So that doesn't really help. But so we figured, well, physicists got a lot of mileage out of Occams Razor, even with an incredibly vague and non-rigorous definition of what they mean by complexity. So we came up with this definition, which is just a simple heuristic which tries to capture some of the essence of Chaitin's ideas for how many bits you need to describe numbers, but has the advantage it's super quick to calculate and it's differentiable, and I can answer questions about it later. But basically, it's just how many bits you need to describe each thing. If a thing is an integer, for example, you get the interesting pattern in the upper right, where 1 or 5/3, etc., are much simpler than a rational number with a huge denominator and an numerator, and so on. And then we try to minimize when instead of using a chi-squared generally to match for our accuracy, or a mean squared error, we use this description length thing, where if it's a continuous variable, you're basically taking the logarithm of your error and summing it up for each thing. And that has a very striking effect of ignoring outliers completely automatically and just focusing on the things that it can fit well even better. So it encourages specialization. And then we combine that with this idea I mentioned, that we actually have an ensemble of models also that compete with each other and each try to specialize in whatever domain they're already doing the best. And because we put together a loss function where we basically take the harmonic mean of the losses. And let me just show you what happens. So we take this data, what we actually put into the computer is just the XY coordinates of the ball at all sorts of different times. And then we train it for a while, and it just automatically discovers this. It discovers that there are 4 different, very simple models that each is most accurate in one of the 4 quadrants. We didn't tell it anything about that there were 4, or what the boundaries were between them, or that there was an outside boundary that was a rectangle or anything. It just discovered that. And within each one, it found very simple rules. It discovered, just as one of you pointed out earlier, that there's sort of circular motions on the lower right. There's an electromagnetic field there. It turns out there is basically gravity in the lower left, and there's a harmonic oscillator in the upper left, etc. But then we don't stop there. Then we take these neural networks, for example, in the regime in the lower left corner, it's basically discovered a solution to this difference equation for how it can predict the next point from the previous 2. And if you look at that little matrix there, as a human being, when it says 1.999999, it kind of feels like the computer is trying to tell you something, right? What is it trying to tell you? that 1.9999 is really supposed to be. Don't be shy, please.
2.
Exactly. Now we don't have to put this in by hand, because that information, the description length Occams Razor definition we gave automatically finds that it can reduce the complexity of this model by replacing that by 2 at a very small loss in accuracy, so that the overall number of bits needed to describe the model and the errors goes down. Now you get this equation underneath, and then you can automatically transform the difference equation into a differential equation, and you've now discovered Newton's law of gravity just completely automatically. So the neural network did the bulk of the work first, get an approximate fit, but then we use additional tools to simplify down the neural network to something, to this really simple thing that does the job. And I'm not going to bore you with a bunch of numbers, but we ran it on 100 different cases like this, and it not only got about 1 billion times less mean squared error, but it also learned faster and required less data because it was less prone. So those equations that I showed you there, how we found, were kind of simple in many cases, like the Lorentz force law or whatever. So you wanted to see if we could do harder ones that were very nonlinear. And so we only had one nonlinear thing in that paper. So this is another project we just finished. It just got published in Science Advances back in April with my grad student Silviu Marinodrescu on symbolic regression. So what is symbolic regression? It's just finding a symbolic formula that matches data that you have. So if you start with a table of numbers, the task is find some formula that predicts the rightmost column from the previous columns. If it's a linear function, that's linear regression. We do it all the time. But if it's not the linear function in general, it's hard. It's probably NP hard, just because there are exponentially many formulas. Johannes Kepler had a one-dimensional symbolic regression problem like this, and it took him 4 years to figure out this ellipse formula, but it was totally worth it, right? Our code discovers that automatically. The problem with any sort of brute force approach is, again, it just takes way too long to keep trying different formulas. So there's a rich literature here. Over the years, people have tried all sorts of genetic algorithms, and the best code out there so far is a commercial package called Eureka that you can get from Hod and Lipson 2009. There's a great science paper they wrote with thousands of citations. But we wanted to see if we could do even better with some ideas from physics. So we took the 100 most famous or complicated equations from the Feynman lectures on physics, stuff like this, and generated just data tables, and then set about to see if we could write code which would automatically discover the formulas using some of those ideas we discussed already. So step one, we did something that the genetic programming people normally don't do. We started by training a neural network to fit the function as well as we could. So now we basically have an interpolator in the 9-dimensional space or 4-dimensional space, or depending on how many input variables there were. And then we do a bunch of tests on this neural network to see if it has any simplifying properties that we can exploit to break this mystery into one or more simpler ones. And let me just walk you through quickly some of the tricks that we use. So for example, if you have a data table representing this formula, Newton's law of gravity, first you can do automatic dimensional analysis. It's sort of obvious, but now you have a data table with slightly fewer variables with this function a divided by b minus 1 squared plus c minus d squared, etc. Now, what do you do with this? Well, symmetries is something that a lot of formulas we care about in science have. So if you have a neural network that can approximate the function, you can easily test if there is a translational symmetry, for example. If this thing really secretly depends on c and d only through their difference, you add a little bit to the input for c and d, and you can see if it really makes a difference or not. And the code automatically discovers that in this case, you have this translational symmetry. So now what it does is it just takes the C column and the D column in the data table and replaces them by the difference. Now you have a new problem with one less variable. So you're fighting back against the curse of dimensionality here. And then we just recursively repeat this. Now we will discover another translational symmetry in this case, that it depends only on E minus F. And then we have another one that discovers that this is a separable thing. It depends only on a function of some of the variables times a function of some of the others, until it can ultimately solve the whole thing. And we put in a number of tests for different kinds of simplicity like this, and plus this basic recursion and a little brute force searcher and so on. And it was able to solve all of the 100 Feynman mysteries, even though the Eureka software could only do 71. So to try to break it, we picked even harder equations from more advanced physics books. Now the Eureka package could only solve 3, and our code solved 18 of them. So we published this, but then we decided to see if we could do even better. So we have another paper we just posted on the archive, which I'll come back to in a little bit if there's time, where we look at even more generalized symmetries. But first, I want to put this a bit in context here. So and talk about this in terms of optimal data compression. Because ultimately, if you're told to fit data, there's always a trade-off between, on one hand, how accurately you fit it on the y-axis, right? The inaccuracy, and the complexity on the other, or your model on the x-axis. So one extreme would be to take a super complex model that just has memorized the entire data set. Now you're going to get 0 error. You've gained really nothing, because all the information is stored in your model. The opposite extreme is to just predict 0 all the time. Now your model takes basically no information to store, but the inaccuracy is huge. It's equal to the original RMS. So the new version of our code, which you can go get on GitHub and run for yourself, will discover a Pareto frontier of all the different formulas that are Pareto optimal, in the sense that there is no other model that is both more accurate and simpler. Now, what's kind of interesting, in science in general, we tend to like formulas that are both accurate and simple, right? And they would correspond to corners in this frontier, convex corners shaped like this, or like this if your screen is reflective. So this is the exact formula in this case in the lower right corner. This is the special relativity formula for kinetic energy. But do you see any other formula here that is in a corner like this? Which one? And is it familiar?
(1/2 mv squared).
Yeah, so it just automatically discovered that this kinetic energy approximation that many of us learned in high school. Not because we told it to do anything special, or we didn't tell it anything about Taylor expansions. It just discovered that this is something which is more accurate and simpler. And this kind of trade-off is something we also use greatly to accelerate the whole search for successful models, because it is a recursive thing, right? And we want to prune so we don't go exponentially wide in our tree. We throw away any partial competitors that are dominant below this emerging frontier. Another thing we did, this is with Hailin Wu again, is looking at this trade-off between simplicity again and accuracy more generally. And we showed that for the case of binary classification, which is a bit easier than finding the formulas, we can actually solve it exactly. This is in the spirit of the information bottleneck a bit that Naftali Tishby gave a great talk about here at MIT recently. Suppose you want to classify, you take as inputs a bunch of pictures, and you're interested in knowing whether they're cats or dogs from a compressed version of the data set of the picture. Now, what's the best way to compress? If you don't compress at all, you've kept all the information there was about its species. On the other hand, if you throw it away completely, you have no information. What's the best thing in between? Well, this is what we found. We derived this formula for how to do it optimally. You can look at the cat and dog example in orange here, for example. you get this very nice trade-off curve, which is analogous to the one I showed you before, where you get these particularly nice corners here, which are desirable because they're both containing a lot of information high up on the y-axis, and they're simple. And they correspond to clusters. The best cluster you can do, it turns out, with a certain number of groups. Normally, people write articles and articles about clustering algorithms, and there's no unique metric to say which one is better than any other. But if you have a case like this, where you're just trying to group your pictures into n groups, and then you're asking what's the grouping that keeps the most information about whether it's a cat or a dog, there is a definite answer to what best means, right? And it's defined by this plane. And I'm not going to dwell on this too much in detail. You can ask me about later. But there are some fun connections to physics that we encountered here, where you get these phase transitions corresponding to different corners, where if you keep tuning exactly the trade-off between simplicity and accuracy, you keep phase transitions corresponding to a new cluster being born. Now, the stuff I showed you here before with looking at data like this and trying to predict equations, on one hand, we were excited about it. But on the other hand, we felt that we were kind of cheating, because we were actually not sending in this raw photos. We were actually sending in to the software, right, X and Y coordinates. And if you're a scientist, one of the most difficult tasks is figuring out what are the relevant parameters in the first place that you should keep track of, right? And what it is that's not relevant. The Schmidt and Lipson paper, which is so awesome, it cheated in exactly the same way. They had video film, but then they themselves measured the X and Y coordinates and sent that in. We wanted to know, could you do better? Could you just start with a raw YouTube video of someone playing ping pong, or a video like this, and just send in the videos? And just have the system tasked with predicting the next video frame, and see if it can somehow discover that what really matters to predict the future is just, in this case, these two numbers, the X and Y coordinate of this rocket, without telling it anything about what the rocket looks like, or that there even is such a thing as an object or anything. So here's what we did. We call it PreRegression because it's sort of the pre-regression step, right? You need to look at the raw video first and do something to it so that you can get those tables of numbers that you're then going to try to find equations describing. So what we did is we sent in a sequence of video images like this, and the goal is to automatically learn how to map that into some sort of latent space, and that we can then run symbolic regression on to discover equations. This is harder than it might sound. It sounds pretty trivial to just write some code that discovers the X and Y coordinates. But the way I've phrased the problem, it's so general that it should be able to solve the problem just as well if you look at the image through a very strange distorting lens here. So now what you want to measure is not at all the X and Y coordinates anymore. You want to do some more weird mapping to get out what the X and Y coordinates would have been like before the distortion, for example. So we struggled a lot with this. It took us about a year to actually get it to work, but Silvio worked hard, and now it does work. The architecture is very simple. We take these images and send them in, and then we have several neural networks here. One, basically autoencoder that maps each image into a latent space, 2 dimensions or 5 dimensions or whatever, and one that decodes it back into an image, which is supposed to be the same one. And then we have this other network, U, that tries to predict the next position in the latent space from the previous 2. And the big problem here is how to define what you mean by simple, because we wanted to use Occams Razor here, right? It's pretty easy to see that if you found anything that works, you can make other things that are much more complicated also that also work equally well. So we first started thinking maybe we could be inspired by this guy in the left here, who defines a simple space as one that has minimum curvature. So you can look at the mapping U, how much curvature it induces in the latent space. But then we realized that actually there's a simple heuristic to this, which is easier to evaluate. You don't have to take so many derivatives. If you just insist on the Jacobian of this mapping U to be as linear as possible, in other words, the derivatives of the Jacobian to be small, then if the Jacobian has no derivatives, then G is constant, and then those Christoffel symbols and Riemann tensor things that you see there, if you know physics, are all zero. So our simple heuristic thing implies Einstein's thing. So we went with that to see if it would be good enough, and it worked actually, except first it didn't. We would have, for example, this rocket moving in straight lines, and the latent space looked like a picture of a cat. When you look more closely at this, it's a topology problem. It would start getting things to work, sort of, but you would have lines that were not supposed to cross that actually crossed, and it couldn't untangle itself without increasing the loss. So we read up a bunch on high dimensional knot theory and realized that if you go, in this case, from 2 dimensions to 5-dimensional latent space, then it's impossible to have any knots for this kind of problem. And sure enough, this worked beautifully. So what we do is we put in a bigger latent space dimensionality than we need from the knot formula, and then we train a bunch, and it has an incentive to simplify itself as much as it can. And then we do a principal component analysis and discover, oh, for example, all the points in the latent space now seem to be lying just in a 2-dimensional plane. And then we can just rotate into that plane, as you see here. And the cool thing is this works even if you looked at the very distorted video, like the one I showed you before. It does not discover this distorted latent space. It still discovers the nice, simple latent space where circles are circles, because that's where the laws of motion are the simplest. This is very much, I think, what our brains do also. We look at the world through the stereoscopic projection distortion, for those of you who do a lot of ray tracing, right? And our brain has figured out how to undistort this and give us an internal representation, which is more like the actual pure X, Y, and Z coordinates. Let me geek out just a tiny bit more on this to indulge my inner physicist here also. So Einstein made a big deal about inertial frames being very special. So basically, the fact that you can actually, if there's no gravity, you can put together a coordinate system where objects in uniform motion stay in uniform motion. And I think our brains automatically discover these, even when we're given data that's distorted in various ways. I think our brain is always looking for the representation of the world that is simplest, where the laws of motion are the simplest, because that's the thing that's most useful for us, right? That makes it as easy as possible for us humans to predict with our brains what's going to happen, which is a key reason we have the brain. So to close the loop, what we did was we gave it all these different videos, and for each one, it mapped it into a latent space. And then we matched them all up together and to have the code discover how they would all be mapped into a single unified latent space. And then there's still some degrees of freedom left here that can be adjusted whatever way you want without changing the accuracy of the prediction. But we have this information theory loss term I told you about in the beginning. So now the code will exploit that to make it even simpler. So it tries translating things sideways so that the equations get even simpler. It tries rotating the coordinate system so the equation should get as simple as possible, and it tries doing shearing so the equation should get as simple as possible. And at the end of this, it actually discovered, for all of the different videos we showed, exactly the equations that we had put in like this, without any 2.99 or different coordinate systems or anything else like that, because this turned out to be the simplest description of it all. And if we had put the equations in a more complicated way, it would have still have discovered these most simple ones. So in summary, what I'm trying to convey here today is I feel that we physicists have not only great customers of machine learning in the sense that we're very grateful for all the cool things machine learning can do for physics, but I also feel that physics has something it can give back to machine learning. And in particular, if you struggle, if you take this challenge that we talked about, where we're putting AI in charge of ever more systems that actually affect people's lives, right? So we would like to be able to trust them more, that they're going to do what we want them to do. Then I feel that this sort of trust should come not because someone wearing a fancy suit tells us to trust it, but because we understand it enough that we trust it. Maybe we can even prove some theorems about it, about the thing, and some bounds on its behavior and trust it for that reason. And the key ideas from physics I've tried to convince you are actually quite useful here. Is one is Occam's Razor, bring information theory into it. Don't just try to minimize the mean square error, but sometimes if you try to minimize something which instead captures how much information you need to store your error in your model, you get results that are simpler and easier to understand, and also avoid overfitting issues. And you can put models on this nice plane here where you can see the trade-off between simple and accurate. And as a human, come in and say, okay, which of those do you prefer to use? I've also said that I think it's this idea of divide and conquer from science is very important. And I would like us to not always instinctively make a single big neural network model and try to make it fit all the data. Sometimes we're much better off from having an ensemble of many models that can each try to specialize in fitting the data in some domain. And then the collective of them can do much better than any one complicated model would. And moreover, now these individual pieces might, some of them be so simple that we can actually understand what they do, right? And finally, for this progression stuff, I think for neural networks, the natural way to quantify how simple they are is how nonlinear, how much the different layers in its curve cause curvature. We found in this example I showed you here that if you just apply that to just raw video, it will actually discover what we humans consider simple, and latent spaces, which are so simple that symbolic regression can then go in and extract the equations of motion. And finally, for symbolic regression, I think what I'm most excited about here is that you can use neural networks not just as the final answer to something, but rather as the first step to modeling a system, as a good approximator. And then you can study the neural network with some other automated code you have, discover simplifying structure and properties and break it apart, and step by step start replacing what your neural network is doing by Python code or something else that you can understand better. And since we have all these tools we've made now that can take data and try to find patterns and find equations that they're described by, we would love to collaborate with anyone here listening who has data that you think might enable some interesting description of a mathematical form. So if you have any cool data that you would be interested in playing around with to see what hidden patterns might be in there, please let me know, and maybe we can work together. Thank you so much.
Cool. Thanks for a great talk. Are there any questions? And again, the people on Zoom can just unmute themselves and ask the question, or send me a message. And then on YouTube, you can just write a comment.
I had an interesting data case, I think, which is I'm interested in small world networks and sort of the flow of disinformation and information through influencers and sort of small world network structures that take place on the internet. Have you ever thought of that kind of data set where we're looking at information being introduced to a network and its amplification.
Very, very interesting. Can you all say your names, by the way, when you ask questions?
Sorry,
we can keep
so
in
we
touch
met
after?
before. Hi, Max. This is Una Mae O'Reilly.
Oh, yeah. You, for some reason, didn't come up on my screen when you talked.
Oh, sorry.
Yeah. So the data, in what form is your data here exactly? Do you have a graph?
Right now I could do all sorts of things with it. That's not so much important as I want to capture the dynamics. And I'm not sure whether, so when you talk about small networks,
Yeah,
that's a structure, right? And it's sort of it's a structural property. And maybe, but I want to, in a sense, understand the dynamics over something with that property. And I was wondering if there's dynamical equations we could look for or something.
Yeah, that sounds really interesting. We're doing some stuff now with graph neural nets, which if you have, presumably you have a bunch of nodes, and then you're looking at how they affect each other, right?
Yep.
Which is very much the essence of what a graph neural net does. And then if we can model the thing like that, we could then apply some of these tools to see how if we can find simple rules according to which the nodes are actually affecting each other. I would love to talk with you more about this, actually. So if you can shoot me an email at tegmark@mit.edu, that would be really fun.
The other thing that occurs to me as a data set would be epidemiology. Right, so we have these very SEIR, we have these compartment models, which are very homogeneous, make homogeneous assumptions. And now people are building sort of agent-based models that are more heterogeneous. And I'm just wondering if there's we know that we believe that there's some very complex set of contact equations and various other pieces in epidemiological models. And I was wondering if you'd given any thought to how you might work on those kinds of models and extracting them from data.
That's also a really cool question. And of course, extremely timely given COVID as well, where it is maybe the most closely related to the thing, cats and dogs things I was showing you, where you're actually looking for useful ways of clustering things. So if you have millions or billions of nodes, of course, the thing is too sparse to be able to model very accurately the exact interaction between each one. But if you start to see that there are certain groups of nodes that can be clustered together because they behave similarly, for example, then you can start getting high enough large enough data quantities on the internode behaviors that you should probably pull things out more in detail. This is not something I've thought very, very much about, but again, it strikes me as a very nice direction to go, because I think the sort of tools I've talked about can avoid the sort of overfitting that you need to not succumb to in situations like that, right? And see what is the clustering that you should make that's actually maximally useful.
Hi, Max. This is Jerry Sussman.
There you go.
Okay, one of the things that's apparent over the years is that amazingly enough, when you do gradient descent, you're not getting stuck in neural nets very much on bad local minima. That the machines seem to be somewhat more unimodal than you would hope. Do you have any insight into that? Does that have anything to do with, for example, things like, well, I suppose things like the fact that at many scales you see the same sort of thing as in renormalization or anything like that? Or is there anything there that makes it clear why that's happening?
Yeah, so it's a really good question about why we don't get stuck in local minima as often as we might think we should. Surya Ganguly at Stanford has a very interesting paper on that. I would highly recommend, where he looks at very high dimensional spaces. This is a little bit string theory inspired, and shows that if it's a very high dimensionality, almost all the local minima will be very, very close to the true minimum. And all the local minima that are much higher loss than the true minimum tend to be saddle points, not actual minima that you can get out of them. That might be part of the reason. But I also think we shouldn't rest.
Again?
Surya Ganguly, Ganguli. But I also think we shouldn't rest on our laurels, because I think we have a long way to go. I think there are many examples where we do get stuck in local minima. And even we did here when we, as I showed you in this progression example in the beginning, where we just could not find that latent space. And in that case, the solution turned out to be add a bunch of extra dimensions first, just so you don't get into this topological entanglement. And then once you've gotten to the low loss, then you can regularize away those extra dimensions and find the true thing. It's hard. You can't. There's a theorem that many of you probably know. It's impossible to tie your shoelaces in 4 dimensions. And in the same way, it's hard for neural networks to get stuck for topological reasons in higher dimensions. And I think I'm speculating now, but I think some of the times when we get stuck in local minima, it's actually for this sort of topology reason. And I can explain maybe a little bit more kind of what I mean by it. Now, the reason you can tie your shoes in 3 dimensions is because to untie them, you would have to move 2 strings through each other. And maybe that's going to cause you a huge loss because there's something saying strings aren't allowed to be near other ones. Or in our case that we had, if 2 different points, because rocket positions get mapped to the same point in the latent space, that's these shoestrings crossing, right? That means you're making terrible predictions now, because in one of the 2 cases, you're putting the rocket in entirely the wrong place. Sure. So these sort of topology problems, I think, cause at least some of our failures to train, and they're temporarily going to higher dimensions, so you can untie the shoestring, and then letting things, using a regularizer, so seeing things simplify out to a more flat manifold, and then get rid of the extra dimensions. That might help.
Okay, thank you.
Yeah, can I ask? Yeah, I'm Shivam. So I was wondering, like, so why, like, it seems like that a lot of your work involves like somehow imparting certain informations that we already know, and like using them like during the learning. For example, we know certain properties about inertial frames. We want to include those information during the training process, or like during building this structure, and somehow like, so have you looked at like how to simplify this procedure itself? Like, let's say not breaking up neural network, like you have this property that you want it to be satisfied much more easily, and then you can automatically figure out structure or neural network structures that would generate, like, construct formulas which already have those properties and stuff like that.
Yeah, that's a very good question. So on one hand, we want to remove as much as possible any human inserted hyperparameters or heuristic biases as you can, right? And just give it the raw data, and with some very simple thing like, oh, come up with the shortest, simplest model that's really accurate or whatever. On the other hand, we know that it's impossible to do that completely because of the no free lunch theorem, right? It's well known that for a completely generic problem, there is no simple way of simplifying it. So this leaves you sort of somewhat philosophical feeling mystery. So like, why can we do any science really if most things can't be simplified? Well, so we wrote this earlier paper this was me and my former grad student David Rolnick and Henry Lin, called "Why Does Deep and Cheap Learning Work So Well?" We looked into this in more detail. So of course, it turns out that the class of mathematical functions that a neural network can actually approximate really well with this modest number of neurons is infinitesimally small in the space of all functions. But this class of functions that we actually care about in physics is also infinitesimally small. And it's basically the same class, which is very, very convenient. So I think it's not cheating for us to put in whatever heuristic biases actually apply to the real world. The truth is, and I'm embarrassed as a physicist, that I don't know the answer to this. I don't know why it is that symmetries, for example, are so important in nature. Nobody really does, but they are. The functions we care about often have symmetries in them. So since we care about our universe, our world, regardless of why it is that way, I think it's fair enough to put that into our AI Feynman code, to study the neural network to see if it has symmetries and then exploit them. Similarly, we don't know why exactly it turns out that almost all functions we ever work with in our jobs can be written as compositions of functions with only 2 variables or less. Like, why is that? Plus and times are functions of 2 variables. Sine and logarithm are functions of 1 variable. Pi is a function of 0 variables. Why don't we need more functions of 5 variables? We don't know, honestly. But hey, this is the universe we care about, right? So we can put that cognitive bias in, and we do, and it helps a lot in our code. So to finish answering your question, I think we should put in any very high level properties that we see apply for whatever reason in our physical world, even if we don't understand physics well enough yet to know why that is.
No, I agree with you. I like, so it's also that like humans think in a certain way, like we have our own biases. So Occams Razor, like it's not like any arbitrary simple function. It's arbitrary simple function that can be understood by humans in a sense, right?
That's
So,
exactly right. And to say it in a different way, you know, if all the data that you could ever measure was like some super advanced crypto algorithm output, so it just looked random, we wouldn't have any brain. It wouldn't be there wouldn't be any point to have a brain. There'd be nothing we could do with it, right? And I think the fact that evolution went with a recurrent neural network for the architecture for our computer is precisely because evolution discovered, hey, you know, that's tapping into the kind of functions that are, or the kind of predictions that can be made in this world we live in. We all know that there are all sorts of other computer architectures you can do also. Maybe some of them are better for implementing certain crypto codes, right? But hey, that's not what we care about so much in science.
So a follow, like a future direction question, a small dude. So have you looked into like program synthesis? Like, so it's like, so say like finding symbolic equations, it's like sort of a simplified version of program synthesis. Program synthesis is like a very complicated problem in itself, but like it seems like certain of these techniques you can use in certain kinds of program synthesis problems. I don't know.
Yeah, I have not contributed anything of value yet to program synthesis, but I'm super interested in it, and I see the stuff we've done on symbolic regression, as you said, as a small stepping stone in that direction, where the only programs we can synthesize so far are these feed-forward functions that can be written down by combining mathematical formulas. But I'm hopeful that some of the ideas we have used, in particular in the most recent paper that I didn't talk so much about, where we discover modularity in the neural network, might be usefully generalizable to a lot of program synthesis questions. Do you work in program synthesis?
Yep. Yeah. Like I sort of try to work in this like area between like sort of understanding machine learning and program synthesis. It's like,
yeah. So Shivam, can you shoot me an email also? I'd love to chat with you a bit at some point
sure.
about this, because I think that there's been a lot of work in program synthesis which takes a sort of black box approach where you just try to train a neural network to output programs, right? But I think this approach that we're talking about might have something complementary to add to that, where you try to discover instead modules and yeah, let's talk.
Yeah, sure. Thanks.
I have a question. So the advantage of kind of this symbolic regression, there's multiple advantages, right? You mentioned interpretability. There's also this extrapolation capability with respect to neural networks. And then there's a high potential of also being more data efficient. But then
yes,
if we use neural networks as a kind of an intermediate step to get this symbolic regression, there's a question of whether we also lose this data efficiency or not. So my question is more like, okay, so for example, to discover this modularity, I think you didn't describe it in the talk, but I read your paper. You analyze the gradient of the neural network that approximates the function to then say, oh, it has this type of compositionality to it. And then, so my question is, do you think you need less data for the neural network to express this compositionality before being a good function approximator? And so that maybe you can still get good data efficiency by using neural networks as an intermediate approach.
So let me see if I understood your question. You lost me a little bit at the end there. So suppose you can, let me put up for everybody what you're referring to, by the way, so everybody's on the same page. So you're referring to stuff like this, right? This is from the paper I didn't talk about, where any function, wait.
I'm not seeing
I don't think you can see it. Yeah, let me try again. Here we go.
Yes, exactly.
Yeah. So any function can, of course, any feed-forward function can be viewed as a directed acyclic graph like this, where information flows through. And most functions that we come across in science are modular, as in this particular illustration here, right? There's only two variables going into that light blue little ellipse, and then only one variable comes out and then goes into another module. And so I think you're asking something along the lines about whether if you discover the modules first, then does that mean?
Now that we have the picture, maybe I can re-express it better. So neural networks are not only hard to interpret, but they're also pretty data inefficient. They need quite a bit of data. And so my question is, since you're using them as an intermediate step, one may think, oh, your approach is going to also be data inefficient. However, you don't need them to be perfect function approximators. You only need for them to exhibit the right compositionality for you to then, say, okay, this is the type of compositionality that it's expressing. So I was wondering if you think those are two data requirements that are different, or maybe no, and the approach is
No, exactly. I think it's very deep what you're saying. I completely agree with it. So, and I think this is a key thing for program synthesis in general also. If you can use a smaller amount of data and realize, well, we don't know yet what the function is, but we can already tell that it's modular, that we can tell already that the only way in which the final function f depends on x and y is that first x and y get combined into something, and then it gets combined with z. If you can just discover that using less data, now you can make a smaller neural network which just has two functions of two variables, right?
Right.
And try to learn the original thing. And you might hope in a more general program synthesis task that you could do the same. And I think that also comes back to this apocryphal Galileo story I mentioned in the beginning, right? Where he was sitting there in the church and felt, well, I don't have full data yet on what the equation of motion is for the swinging chandelier, but it seems like our universe is kind of modular, that to predict the future angle of the chandelier relative to the vertical, it doesn't really matter what the priest is saying. The only thing that depends on is the previous position and velocity of the chandelier. Our human brains, I think, are very good at picking up on this sort of modularity, even before we've figured out what the modules actually do. Right? The whole fact that even little babies are very quick to pick up on the idea of objects, for example, and that certain things are independent of other things, more or less, I think captures that again. And so I think it's very wise and deep what you're saying, that this can be a really powerful route to data efficiency, and you can probably discover modules that are useful long before you know exactly what they do.
Mm-hmm. Cool. Do we have any other questions? Cool. So we've also passed 3 p.m. So let's leave it here. Thanks all for coming, and thanks Max for a great talk.
Thank you so much.
Okay.
Goodbye.
Oh, Max, I want to say something more to you sometime.
Yeah, sure. It would be fun to continue the conversation. And any one of you who wants to talk more
Well,
about
you said
this.
something about, you said that that we're using binary functions, but of course that's not quite true, because if you look at things like the fact that we invent vectors and then tensors and things, we're actually generalizing things into functions of many variables.
Absolutely. I absolutely agree with that. And of course, matrices and differential operators and so on. But there again, though, I think you'll agree there's additional structure again. If it's a vector, you have this symmetry.
It's not at the level of plus and times.
That's correct. Absolutely correct. So I think you'd agree. There is, for some reason, we can get away with simpler things than you might think we need to get away with. And if you think you know why that is, I would love to know, because I don't feel I do.
Let's talk about it.
Yeah.
Okay.
All right. Goodbye.
Night.